All right, I will begin. Dear Father, we thank you for this day. I thank you for these students. Pray you bless this class today, Lord. In your name I pray. Amen. So is it parking or convocation that got you?
Convocation.
All right, so I think maybe we should start meeting at 12:05. And we'll go to 1:05. Sound good? Should we do that? Oh, you have class at 1:05? Oh. Would you go for 12:05 to 12:55? All right, let's do that. All right, so these are the functions that I've asked you questions about in the homework, give or take. The first is the principal nth root function. This is the principal argument. This is the complex exponential. As you can see, it's defined in terms of an ordinary real exponential and cosine and sine. All right. The next thing you could introduce would be the complex logarithm function. That's defined in terms of the ordinary log function of the modulus plus I times the argument of z. Of course, the thing to remember here is that minus pi is less than argument of z is less than or equal to pi, where z is equal to what? Modulus of z e to the I arg z. I mean, so the argument is just the polar angle, the standard angle, which happens to fit between minus pi and pi included. So we use that to define both the nth root function, principal nth root function, as well as the principal logarithm. Now, both of these are in some sense ad hoc choices, all right? They're ad hoc choices in the sense that if you look at the equation which motivates them, the equation which motivates this basically is just looking to solve, z to the n, w, maybe, I'm trying to think here. If I have w to the n equals to z, and I solve for z, yeah. So that is one solution to the Brown equation. There are in fact n others, all right? Those n other solutions we can obtain by multiplying by the principal root of unity as we described last time. Now this right here is a solution to what? If we have w equals to e to the z, one solution to that is in fact w equals to log z. Oh, excuse me, I did that backwards, didn't I? I'm sorry, guys. I'll get it eventually. If we solve that for w, what do we get? This implies that w is equal, well, let me just say this. W equals to log z is one solution to that equation, but it's not the only one, all right? So, I mean, really, this implication should be and many other possibilities. Or I could just draw the arrow in the other direction? Sure. So in fact, if you want to say, let's see here, how about this? Z in the complex plane such that, oh, good grief. W, I have a problem here, obviously. W with what the role of Z and W gets intertwined in my head. But w in the complex plane such that e to the w equals to z, all right? This is little log of z. Little log of z is the set of all solutions to the equation z equals to e to the w. All w that solve it. Because you can prove that e to the little log of z in the sense of taking the image of a set that's just equal to z again. All right? Now, let me just expand on that thought for a minute. What I mean by what I just wrote down. So if we look at little log of z, I told you guys, and we could derive this, but I'm just going to write it down for the sake of brevity. So if little log z is natural log of z plus I times the argument of z, all right? Remember that little arg z is what? It's the set of all possible standard angles. So we could say that's arg of z plus 2 pi z. So little arg is a set of all possible standard angles that geometrically are the same as the principal argument. Principal argument plus all possible 2 pi multiples of it. That's little arg. So what happens if we take, let's say, some element of this set, let's call it, W. Suppose W is in little log of z, right? And consider e to the W, what's that equal to? That's e to the natural log of the absolute value of z plus what? Plus, I times what? Well, apparently, argument of z, right, which is a specific fixed thing, and then plus what? What's a typical thing in the argument of z? It's the principal argument plus 2 pi j, right, where j is some element of the integers. So this right here is a typical point in the little log, right? Notice if we put j equals to 0, it returns the principal logarithm, the capital log. But there's lots of other stuff in here. Now what happens when you calculate this? Well, we get e to the natural log of the modulus of z times e to the I arg z times e to the I, times 2 pi j, right? Using the laws of exponents, which you can prove, or maybe I should make a homework problem since I'm not sure you guys really understand what I'm writing. Maybe I should make that a homework problem. But you can prove that, in fact, this complex exponential has the usual laws of exponents. The reason that's true is the combination of the adding angles formulas for sine and cosine and the ordinary laws of exponentials for the real exponential. I'll probably make that, that'll probably be in your mission too. That's a good problem to work through. It's not that hard, but. All right, so this is just straight up modulus of z and e to the I arg z. What do we got then? What about this? Well, that's 1, right? Because any 2 pi multiple fed into the imaginary exponential gives you cosines and sines of multiples of 2 pi, which are both, the cosine is 1 and the sine is 0. So this just reduces to 1, and we're left with z. So that shows you that every single element of the little logarithm, right, the set little log, they all solve z equals to e to the w. This is the meaning of little logarithm. It's a set of all solutions to z equals to e to the w. There's more than one solution because the imaginary exponential is not injective. It's not one-to-one, right? So that departure from injectivity means that there's more than one way to solve for w. If you're just after one single ordinary solitary solution, then this does perfectly nicely for you because this is the principal logarithm. It's just one particular solution to z equals e to the w, right? Now, other functions I define after that in chapter 2, the cosine, the sine, the hyperbolic cosine, and the hyperbolic sine, these are all defined in terms of the complex exponential, all right? So I'd encourage you to read what I've written about that. I told you a bunch of properties of them. They're a lot like ordinary sine and cosine, a lot like ordinary cosh and sinh, but they do have some surprising new features, like cosine of an imaginary number can be arbitrarily big. Sine of an imaginary number can be unbounded in magnitude, right? In contrast, how about real sine and cosine? Well, they're at most 1 or minus 1, right? I mean, the magnitude is less than 1. That's not true for sine and cosine in the complex case. However, despite that, it's still the case that cosine squared plus sine squared is 1. So we have this funny situation where we lose certain features of the real analysis of sine, cosine, cosh, and sinh, and yet we retain many of their privileged and usual expected algebraic identities. All right. Now, I've got a lot more to say about this material, but I'm going to make a video about it because most of what I have to say involves graphing and like tracking pictures, going to pictures, and it's just better if I do it with marker and on paper and also just because if I put it on YouTube and you're bored with what I'm saying, you can put it on double speed and still get what you need out of it and not suffer through me drawing the wrong picture and then erasing it and starting over again in class, right? So, and then there's the real reason, which is that Convo held us up Wednesday and it made me turn a 5-minute proof into a 20-minute proof and then everything fell apart, so. All right. Nope. Exponential is not multiply valued. Exponential is single valued. I think I say if possible find. I think if you read the wording should say that it's possible that those things have multiple values, but it may not. Part of the point of that question is for you to come to an understanding. Am I asking you to find a single value, or am I asking you to find a set of values? If there's a typo there, send me an email though. Yeah?
So since they use a principal argument,
If you have the problem, I'll look at it in a second here.
are the principal root and principal logarithm functions not continuous?
We will talk about continuity later. That involves questions of domain, which is exactly what I wanted to address in that video I'm talking about. There are subtleties there. Yeah. Well, so what was that? Did you have the homework handy? No? Oh, okay. Well. All right, so that brings us to chapter 3. And again, there's a lot I've written in chapter 2 that I don't think will make a lot of sense to you yet, because I haven't even asked homework about it, right? I talk a bunch about the local, like the restriction and finding a local inverse to a function, if you've read those parts of the notes. Maybe you haven't thought about those ideas before. So if you haven't thought about those ideas before, there's something big there for you to learn in terms of mathematics. And I'm not sure that matters to us that much right now. It's just as a question of organization. It's where I put it in the notes. What I really want you to learn right now, it's in your mission 1, right? That's the stuff you need to nail down as a starting point. Issues about domain and continuity, that other stuff, that's a little bit later. Although, I have discussed, I think, some of the domain issues in chapter 2, that's true. All right. So, as I've mentioned, this class is, yes, a complex analysis class, but I'm trying to do a little bit more. I'm trying to expand our view to include a few other cases, all right? So more than just complex numbers, what are other number systems? And so chapter 3 I've just called numbers. And so what I'm trying to do in this chapter, numbers, good job, numbers, goodness gracious, is to describe some other number systems, all right? And so let me just rattle off the formal definition for you. So here's the definition that we'll use. We'll let A be Rn. You guys know what Rn is, I'm assuming. This is, of course, n tuples of real numbers, right? You've studied R2 and R3 in Calculus 3, right? But it's Rn paired with a function, let's just say a multiplication. And for the sake of this definition, I'm going to use a star just to draw your attention to the novelty, to the new thing that's going on here, okay? But we will often omit the star and just use juxtaposition in examples, like we've been doing with complex numbers, all right? So, and this multiplication satisfies the following axioms. Number one, number I, it's bilinear. Number two, it's associative. Number 3, it's unital. And we say x, an element of A, is an A number. Right? If x times y is equal to y times x for all x and y in A, then A is commutative. Now, I just use words. Let me write down what do I mean by bilinear? I mean that this multiplication satisfies those usual rules we're used to, right? Like x times y plus z, you know what it is, right? What is it? It should be x times y, right? Plus x times z. And also, if we did x plus y times z, we get what? We get x times z plus y times z. So these two things I just wrote down are additivity, but when I say bilinearity, I mean additivity in both senses. And another thing, I also want to be able to pull out real scalars. So also, we need like x times some real constant times y is equal to the real constant times xy. And also, if we have a constant times x in the first slot, we can pull that constant out front like that. So this here, I'm assuming that c is a real number. All right. So that's bilinearity. It says we can distribute either left or right sums like you're used to, and you can pull real numbers out. All right? That's one thing we're assuming a number system has. The other thing we're assuming is it's associative. What does associative mean? Can you guys tell me? So there we would have x times y times z makes sense, right? So associative in this sense, it's multiplicatively associative. We're also going to use the addition that's already on Rn, like vector addition. We're still assuming that that's there to use, right? In fact, I'm using it right now in these statements. What does unital mean? Unital means that there exists a 1 in A such that 1A times x is equal to x is equal to x times 1a. And this 1a sometimes we'll just denote by 1. Often I just denote it by 1. It's the unity in the algebra. All right. So this is our general concept of what a number system is. In words, it's a unital associative algebra. To be more precise, it's a real associative algebra of finite dimension with unity. For example, complex numbers are such a thing. All right, so like complex numbers, we just put a equals to R2, right? And if we have, x plus iy times a plus ib, that's what I talked about in previous classes, right? Of course, we don't write this, right? We omit this, right? Omitted for our complex example. So we just use juxtaposition rather than something star something for the complex example. But we also use this terminology, right? X in the complex numbers is called what? A complex number, right? So let me give you some other examples, and then I'll get into some more of the general way we can think about this. So here's the other two primary examples I have in mind for you guys are as follows. So let me, again, just to reiterate, example 1 is a equals to the complex numbers as usual. And again, just to summarize, that's at least 70, 80% of this course, right? 70, 80% of what we do in here is that. The second example, it would be A equals to, well, I call it H, and this is, as a point set, it's R2, but with the following. So we say x plus jy is an element of H, right? And define, here's the way it works, x plus jy times A plus jb equals 2. And so here's a quick way to remember, these are called hyperbolic numbers, all right? The hyperbolic number system. So essentially, if you want me to just summarize it briefly, we're going to assume that this j, you could say, well, the hyperbolic numbers are just like ordinary numbers, except you add this unit j, such that j squared is equal to 1, right? And j is independent from 1 itself, in the sense of linear independence. So it's a two-dimensional thing, but essentially it's just governed by j squared equals to 1 and proceed normally. So, you know, multiply this out. By definition, this is xa plus yb plus j times ya plus xb. Well, excuse me. Yeah, ya plus xb. I mean, you could do it in a different order. But anyway, there you go. That's so-called hyperbolic number multiplication. And you can study the properties of this system. I mean, that definition for multiplication, you can work it out. It's commutative, it's associative, all right? It's got a copy of the real numbers in it, all right? What else can we say about these hyperbolic numbers? I mean, what have we done so far for the complex numbers? We've done what? We've tried to find multiplicative inverses, right? What would happen when we try to find a multiplicative inverse for a hyperbolic number? Let's try it out, see what happens. So what would we have to solve? If we're looking for the multiplicative inverse of x plus jy, let's say that the inverse we're looking for is a plus jb. What should that be equal to if we're looking for, so I'm thinking of this thing as being z, so to speak, okay? So if this is going to be z inverse, what does the multiplication of z and z inverse have to be? By definition, we want it to work out to 1, right? So I just gave you the definition for that multiplication right above. All we got to do is set this equal to 1, right? Now, I just said a minute ago that 1 and j are independent. In this number system, essentially, we're using the following notation. 1 is 1, 0. J is 0, 1, right? Just like your first homework problem is based on trying to get you to understand more deeply that I is based on using the notation 1, 0 equals to 1 and 0, 1 equals to what? I, right? So in the same sense, 0, 1 here is the j. But my larger point, what I'm trying to say to you is that this, right, and this are independent. That's like the x component, that's like the y component, and you can match them up, right, to the x and y component to the right-hand side, which are 1, and it's harder to see, but if you look carefully, you can see that there's a j times what? 0, right? So it looks like we have two equations, right? What are our two equations? We have xa plus yb equals to 1, and we've got ya plus xb equal to 0. We should think of z as being given, right? Z is given. So our unknowns here are a and b. So if you like, you can rewrite this as the matrix problem. X, y, y, x times ab. We're trying to solve for ab. Do you guys know how to solve a 2 by 2 system like that? Certainly we could do elimination. You could do lots of different things. I recommend multiplying by the inverse, the 2 by 2 matrix inverse. If you didn't know already, the inverse of this matrix is what? So you take the 1 over the determinant of the matrix, and you flip the diagonals, which is really hard to see on this one, and you put minuses on the off diagonal. And so that's a known formula for the 2 by 2 inverse. So if we multiply this by that, this implies that AB is equal to 1 over x squared minus y squared, x minus y x times what? 1, 0, right? What does that work out to? Let's see here. You may or may not know how to do this. I'm happy to talk to you about it in office hours if you don't know how. So this column vector times that matrix gives me an x, and then I got a minus y. So in summary, we found A is equal to x over x squared minus y squared, and B is equal to minus y over x squared minus y squared. Hence, Z inverse is actually equal to x minus yj divided by x squared minus y squared. So there you go. We just worked it out. That is the formula for the multiplicative inverse of a hyperbolic number, which we can derive by brute force, like I just did. All right. Now I want to show you kind of a more intelligent. This is not bad, I mean, but there are other ways to think about finding the inverse than this. Let's stop and smell the roses for a second here. What happens when x equals to y? What about y equals to minus x? Y equals to x, y equals to minus x, both of these? That's no bueno. I mean, we got division by 0 there, right? In contrast, if you look at problem 1 in your homework for complex inverse, you got division by a squared plus b squared, right? Or if we were to do the same letters, it would be x squared plus y squared. But when is that not defined? Only when x and y are both 0, right? So if you look at the complex numbers, like any z out here, z inverse exists, right? As long as that z is not 0, right? Only 0 is missing. So like every non-zero complex number has a multiplicative inverse. If we were to draw a picture of the hyperbolic numbers, right? So suppose this, typical point here, z equals to x plus jy. Which hyperbolic numbers have multiplicative inverses? Apparently, we've got to avoid these two lines here, right? Y equals minus x, y equals to x. Those are trouble. We have no multiplicative inverse there. Those are what are called, the points along those lines form what are called zero divisors, all right? So here's my notation for that. Zero divisors of the hyperbolic numbers, it's equal to x plus jy, such that y is equal to plus or minus x. That's basically what we just showed. Here's a specific example of that. For example, if you look at, this is 1 plus j. So if we look at 1 plus j and we look at over here, 1 minus j, what happens when you do 1 plus j times 1 minus j? You get 1 squared plus j minus j squared, which is? 1 minus j squared, which is otherwise known as 0. So these are non-zero hyperbolic numbers, right, whose product is 0. Is this familiar? No. This is far from familiar. You're not used to working with numbers like this, right? Unless you're like into modular arithmetic. In that case, you're like, well, this is fine. In Z6, we have 3 times 2 is 0, right? It's no biggie. But that comes at a price, right? When you work with a number system which has 0 divisors, you have to be aware of 0 divisors, and they mess things up. Much of the analysis that we know for real and complex variables is partly built on the fact that complex numbers form a field, and the real numbers form a field in the sense that every non-zero element has a multiplicative inverse. The fact that these don't will change things for us. So that's one of my first and most important examples, all right? You can build on this, though. So this is example 2 to the 2.n. I don't know what you want to call this. But if we have this other thing, hn, it's defined to be things of the form. So basically, you do like a0 plus a1j plus a2j squared, plus oh, I'm sorry, I messed up my numbering. I usually put a 1 on. It doesn't matter. I'll stick. You guys already wrote that down. I'll keep with a 0. If I do that, then this is, yeah, that's fine. That's fine. I'm sorry, guys. I'll get with it. I'm just quibbling over notation. Like that, such that all the a's are real numbers, and j to the power n is equal to 1. These are called the n hyperbolic numbers. You can prove, and how do you multiply those? Like I said, you proceed as normal. I mean, you multiply them like usual, subject to the rule j to the n equals to 1. All right, that's how we do it. Here, I'll give you a sample calculation since you guys are being nice today. Just kidding. 1 plus j times 1 plus j squared. And here's a sample calculation in H3. The 3 hyperbolic numbers. So if I take this, if I multiply these like so, we get, maybe I should put some numbers in here. I'm going to put a 2, and I'm going to put a 3 over here so you can see better what I'm doing, okay? So 1 times 2 gives me 2, plus 3j squared, and then plus 2j, plus 3j cubed. So we just distribute like normal, and then what? Collect things, right? J cubed is 1, so we actually get 5 plus 2j plus 3j squared. So there you go. There's a typical product in the 3 hyperbolic numbers. So this is another number system you can consider. If you're interested, by the way, this has some connection to special relativity. You can think of these as like being the light cone. Papers have been written about this. Some people call these Lorentz numbers because of their connection with like special relativity. I'm not sure what a good application is of the nth hyperbolic numbers, but I do have some applications I'll show you as we go on. I will tell you this is actually what's called the group algebra of the cyclic group of order n, which doesn't have to make sense to you right now, but maybe it will later. Again, this is not a field. Lots of 0 divisors in here, all right? Yeah.
Is it true for all of the n hyperbolic numbers that the non-units are always 0 divisors?
Yes.
Is that specific for the n?
In any of our associative, in any of the algebras we study, there are 3 kinds of things. There are units, there is 0, and there are 0 divisors. There's always this trichotomy. And part of the reason for that is because we have an isomorphic copy of the algebra, which we're going to call the regular representation. And that regular representation is a set of matrices. And those are real matrices. And those real matrices either have determinant non-zero or determinant 0, right? And so that corresponds to the matrix either being invertible or being singular. If it's singular, that means it corresponds to a zero divisor or is just straight up zero. And that's why there is this trichotomy. It's one way to look at it. I mean, there's probably another more elegant algebra kind of thing, but
How you got you have 2 plus 3j squared plus 2j. So what is j? Can you please explain like how you got the equivalence to the right side? So you did the factoring. You did FOIL.
sure, this times this gave me that.
Get that. Perfect.
This times this gave me
And then how did you get to
that.
the middle section to the right?
So here I commute the 2 and the j. So j2 is 2j. And then 3j times 3j squared is 3j cubed.
Yeah. Okay, so then how did you get to the next one?
So here, this is just 3 because j cubed is 1 in H3. See, that's the main thing is you could say that this is really, some people would even denote it this way. They'd say this is just, this is generated by j such that j cubed is equal to 1. That's something that people who were, I mean, that would be a short description of what's going on.
Thank you.
Yeah. Okay, so now I'm not going to describe for you right now precisely. So one of your homework problems actually is to find the formula for the inverse in H3. All right, now that's a little bit, that's kind of a hard, that's not as easy, that's not an entirely easy calculation. It's not impossible either, but that means that you need to go through the analog of what I just did here. You're going to have 3 equations and 3 unknowns with a matrix with 3 letters in it. But it's a relatively simple matrix, right? All right, n hyperbolic numbers. By the way, what's H2? H2 is just H again, right? So if I just say hyperbolic numbers, I mean n equals to 2. Example 3, so-called dual numbers. Dual numbers, one application for dual numbers is sort of just as a heuristic, sort of back-of-the-hand model of infinitesimal calculus. What's epsilon? Epsilon's really small. What should epsilon squared be? 0, right? So the dual numbers, which I typically use gamma for, these are things of the form x plus y epsilon, such that x and y are real numbers, and epsilon squared is 0. So what does the multiplication of these look like? X plus y epsilon times a plus b epsilon. How's that go? We've got xa plus yb epsilon squared plus ya epsilon plus plus xb epsilon, I suppose. Cleaning it up a bit, we've got xa plus epsilon times, xb plus ya. I mean, however you want to group them, it doesn't really matter. There you go. So these are so-called dual numbers. What do you think the n dual numbers would be? In the same spirit, we can define the n dual numbers. They're built with some epsilon that when you get to the nth power, it's 0, but up until then, it's non-zero. So the n hyperbolic numbers are an n-dimensional algebra. The 3 hyperbolics are a 3-dimensional algebra. The dual numbers are a 2-dimensional algebra. The n dual numbers are an n-dimensional algebra. All right. And when I say dimension, I'm talking about dimension in the sense of usual calculus 3-dimension, like a 2-dimensional or 3-dimensional thing, all right? Or if you've had linear, I'm talking about real dimension. So these are the main examples that I want to look at calculus on as we go on, all right? But I took some time to try to develop the theory of associative algebras in a little bit more generality for you guys, all right? So I want to talk about that now. Now that we have a little bit of examples, now let's get into trouble with some theory. Well, no, let's get out of trouble with some theory. How about that? Now we have 9 minutes. So in the interest of not making me regret my life. Let me use the projector here, if I can. Come on. Hello? Hello? Ah, hello. All right. Well, are you gonna show it up? What you doing? I got something for you. Come on. Be a good projector. Oh, look. It's actually not green. They must have replaced that. I remember this room being much more green before. Yeah. Man, look at this. I don't even need to turn off the lights in here. I must have taken some of that $1 billion we're sitting on and bought a projector. Hooray. Okay, so here was the definition I wrote on the board for algebra, right? So to study this algebra, what you really want to do is you want to look at multiplication maps on the algebra. So this is L sub alpha is a left multiplication map. It's just defined by, you take and you multiply by alpha. That's the definition of this map, all right? It turns out that left multiplication, essentially you can identify with alpha itself. That's the big idea here. But if you take a set of all left multiplication maps, that's called the regular representation. The matrix regular representation I was talking to you guys a few minutes ago is simply the set of standard matrices of these regular representation maps. So if you've had linear, show of hands, who has not had linear? Okay, so I understand I'm going to try to help you with the homework, but how many of you are also taking linear right now? Well, for you three, it's especially helpful then. For the others of you, when you get to linear, there's part of it you're going to be bored. I don't use anything too deep. Really, I'm just going to use the idea of standard matrix. That's most of it, okay? And I actually define it in here. We'll get to it in just a second. So first of all, my first proposition, write a linear. What's this mean? This means that I can pull an algebra multiplication out of the map. So t of x times y is t of x times y. And so the first thing I prove is that a mapping is right linear on the algebra if and only if it's in the regular representation. Another way of saying this proposition is that every right linear map is actually a left multiplication by an algebra element. All right, so I'll let you read the proof of that. Since we have a lot of people here who have not had linear algebra, I'm going to try to focus on that aspect of it a little bit more than I would otherwise. So it's easy to show that the left multiplication maps are linear in the sense that they behave like a derivative or a limit or an integral, right? You can break up against sums and you can pull constants out. This is what linear map means. Here's the proof. If I have cx plus y, I can, by definition, that's alpha times cx plus y, but by the definition of the algebra, I can pull the constant out using that bilinearity we talked about. And so I've got c times alpha x plus alpha y, which is c alpha. So this is exactly c times L alpha of x plus alpha y. So this proves that the left multiplication by alpha map is in fact a linear, what's called a linear transformation. Now the beautiful thing is, in linear algebra, we learned that any linear mapping from Rn to Rn has a formula in terms of matrix multiplication. In fact, that's an if and only if. A mapping from Rn to Rn is a linear map if and only if its formula can be written as a matrix multiplication, an n by n matrix, which is a box of numbers times a column vector. And more than that, that matrix has a name. It's called the standard matrix. How do you find it? Here's an example. So here's a function from R2 to R2. We have a pair of inputs, a pair of outputs. This is a mapping from R2 to R2. Here's the formula. I made it up. x plus 2y, 3x plus 4y. I'm a creature of habit. I like 1, 2, 3, 4. Now, this is my stupid notation for this column vector, all right? Because I don't like putting column vectors in the middle of sentences in text. Okay, great. Now, going from here to here, that's the definition of matrix multiplication. So this 1, 2, 3, 4 times that xy is equal to this and that. And once you write that, whatever's here, that is the standard matrix. That's it. That's it. Now, there's another way you can find it, though. If you don't like doing it that way, you can also calculate the standard matrix by simply feeding the standard basis elements into the transformation. You put the first one in to get the first column, you put the second one in to get the second column, and so forth. And so if you plug in 1, 0 into the formula here, 1 plus 2 times 0 is 1. 3 times 1 plus 4 times 0 is 3. So that's why I get 1, 3 for the first column. Plug in x equals to 0, plug in y equals to 1 into this, you get 2, 4. And so again, 1, 2, 3, 4 is the standard matrix. You don't need 3-hour math course to learn this, right? I mean, this is not why people have trouble in linear algebra. It's all that pesky linear independence spanning proofy stuff, right? You're like, I wish that linear algebra was just what you just said. That would be lovely, but it's not, is it? It's more than that. Is pain and suffering? I guess I'm a sadist. Let's see here. So, I guess I don't need to edit that. So the standard matrix, actually I think saying I don't need to edit that makes it worse, right? I don't know, but yeah. Now that's like a meta editing comment. If I made another one, then we'd be like, it's like we're getting into some sort of like, what's that movie? Inception? Yeah, we're getting into an inception of commenting comments. Let's see here. Obviously, I'm digressing. Okay, so the matrix representation of A is, like I said, the set of all standard matrices for left multiplication maps. So M sub A is my notation. It's the standard matrix of T such that T is an RA, which is another way of saying that T is. So now, specifically, what you're going to do to calculate the left representation, a typical matrix in there, you take alpha times E1, alpha times E2, alpha times En. That is the representation of the number. All right. So the nicest case, in fact, everything I've written so far, all the examples I wrote on the board, the identity for the algebra was the first standard basis element. So like 1, 0, 0, 0 is equal to 1. In that case, the first column in the regular representation is just the number that we're representing. And so the standard, the representation you calculate just like this. It's very simple. Here. A stupid example is 3.16, where I point out that a real number is its own regular representation. Yay. Complex numbers is more exciting, though. So here's our complex number, a plus ib, which is really ae1 plus be2 in our notation. So the representation of that, the first thing is a plus ib. Then I take a plus ib times e2, but e2 is I. So that gives us a plus b, ib, and then minus b plus ia, which is this matrix, which you have seen before today. Wait a minute, maybe not today. No, you didn't see this today, but you've seen this somewhere, because I like it. Oh, I wrote it last class. I said that that was a model for the complex numbers.
Wait, was it last class or was it
Monday. I'd like to forget about Wednesday. So, so in this way of thinking, you could calculate the inverse to the number by calculating the inverse of its representation and then tracking back. The inverse of this 2 by 2 matrix is 1 over a squared plus b squared, a, b minus b like that. And then if you look at the representation, I mean, that is the matrix representation of that, which you recognize as the reciprocal of a complex number. So my point to you is we can find the inverse of the matrix to find the inverse of the number. One more thing and then I'll stop. So properties of the, well, I'll say more about that next time. I just, while I had this out here, I'll end with this. Here's the hyperbolic numbers. What is the regular representation of the hyperbolic numbers? So you have a plus bj for the first thing, and we take j times a plus bj for the second thing. J squared is 1, so it gives us b plus aj, which is this matrix. Isn't that neat? We've seen that matrix when we were doing the algebra here already. It's just because it's kind of the same math, so you're going to end up running into it, but that matrix is essentially, can be thought of as a hyperbolic number. And the inverse of that matrix would allow us, we could find the inverse of this matrix and find the number which was represented by that inverse matrix. That would give us the inverse of the hyperbolic number. That's the other way we could calculate. We could find the inverse of the matrix rather than finding the inverse of the number and then track back. All right, I will say much more about this representation idea next time. So have a good weekend, you guys.